so we can understand the new stuff. Okay. Well, that's a little selfish.
Yeah.
I'm coming around like a super fast stealthy ninja.
I didn't even study my hair. There's no one in my class doing it. There are, but no one has it. Oh yeah, exactly.
Okay, my loves. When I say talk to groups about chemistry, I need you to talk about chemistry. Talk about chemistry. I don't know what chemistry.
Okay. Let me know if you can't find it. If not, pull out as many 50 milliliter volumetric philosophy you can find and a bunch of salt. That's it. All right, ladies and gents. Matt, tell me something about one of your favorites.
I'm personally a metallic guy.
You're a metallic guy?
Yeah. It doesn't dissolve.
Doesn't dissolve. Okay, so not soluble. Look at those vocabulary terms. Not soluble. Scott, give me something else.
Covalence.
Low melting point. Paige.
Ionic soluble.
Soluble always or soluble in water? So if anything, we can definitely say they're probably soluble in water. Allison. Okay, so I'm going to say attract via IMFs, so intermolecular forces. Good. Melanie, give me something else. lattice, like lattice pattern is basically a cation, anion, stuff like that, right? So I'm going to add to our list here and just say they have ions in them. You're like, duh, ionic, right? Aaron, give me something. Aaron.
Oh, sorry. For metallic, they are conductive.
Ooh, conductive. And this one's something that we don't always differentiate, but is it conductive in its aqueous state or in its solid state? Solid state. Right. So which of these are conductive in their aqueous state? Ionic, right? So ionics make ions, and if ions flow free, and if the ions flow free, they're able to serve as an electrolyte. So this one's going to be conductive in the aqueous state, and I'm going to put the term here, electrolyte. So we start to use that term to describe something that's conductive in aqueous state. Brandon. I know we're getting a lot of ionics. Give me some covalents and metallics. Right. So everything's going to be pretty opposite between ionic and covalent. So these would be. I'm actually going to use the word insoluble. Insoluble in water for covalent. Madeline, give me something else. Ductile, okay. Matt, give me something else. Malleable, okay. Eli. Okay, they don't have ions, so how about we say instead they're made of nonmetals? Okay, so these are going to be all nonmetal elements. So counter that. Hold on, I can't counter that, Allie. If the covalents are made of non-metal elements, what are ionic ones made of? Metal and non-metal. And everybody, metallics, made of metal. You're like, okay, cool. How about what does the term volatile go with? Which of these?
That goes with covalent.
Right. Volatile means that it's going to vaporize easily. And if you vaporize easily, that means you're going to be having usually a pretty low melting point, which is what that one, or vaporization point, which is what the top one up here says. And you can put melting point or boiling point up here. Countering this, we didn't say over here yet. Nope, not at all. These have ionic ones have a high melting point and boiling point. What about metallic? High or low? High. Do metals just, well, okay, I don't want to say this broadly generalizing, but do most metals just like melt when you put them on the stove or melt in your hand? No. What is one that does melt in your hand? Okay, mercury is already a liquid, but gallium is actually one that melts in your hand. Gallium will, it's solid at room temperature, but will melt if it just gets a little bit warmer. So these are going to generally, they're going to have a high melting point and boiling point. There's something special about the way the electrons exist in a metallic bond. Okay, charades, ready?
Wave. C
of delocalized. I was going to go like everywhere. Okay. C of delocalized electrons. What? Oh, dang. I was just going to say mobile electrons at first, but C of delocalized electrons is easier to do characteristics for. So these have more static electrons. These are non-mobile electrons. Okay. I think that's a pretty good list. Anybody have anything extra? Say again? Okay, so these are non-conductive. That's pretty, yeah. Non-electrolytic. So yeah, we didn't capture that, you're right. So this would be non-electrolytic, meaning that they're non-conductive in aqueous state or in solid state. Okay, and then ions definitely are in the ionic ones. Molecules would be the term that we could use to describe a covalent compound, And a lattice is actually how we describe a metallic compound. So you guys remember a lot. I'm so proud of you. Okay, this is usually the part they're like, oh my gosh, I forgot the difference. But you guys did a very good job. I'll show you those. Okay. So tell me of these. Look at the first three categories, 1, 2, 3. Which of these? Okay, let's classify those. Ionic, covalent, or metallic. First one, ionic, metallic, or covalent. Ionic. What's the formula for that? HCO3. Good. NaHCO3. Sodium bicarbonate. This one's ionic. Okay. How about this one? Sucrose. It is covalent. Good. And sucrose is similar to glucose. What's the formula for glucose? O6. Sucrose is actually C12, H22, O11. It's not quite a 1:1 ratio, but it's really close. Okay, so these are covalent, and then sodium chloride, I'm not even going to ask, NaCl, sodium chloride, 1 plus 1 minus, that's ionic. So which of the three above would be conducted in solution? So 1, 2, or 3? 1 and 3, because they're all ionic. So just basically make sure you can match a solution solvent-solute interaction to the properties that they would exhibit. So this is 1 and 3 because it's ionic. Dissolves in solution would be who? So the word dissolves is kind of weird, right? So when I say dissolves, think back to Kool-Aid or making sweet tea. What do you put in there? Sugar. Does it just clump up at the bottom? You're like, okay, bottom's up. What happens? You stir it, and what happens? So you're saying it dissolves, right? Well, sugar is made of what? Say again? Sucrose. Sugar is so table sugar is sucrose. So we all experience sucrose actually dissolving in water. So if I asked you to salt dissolve in water, you're gonna go, yeah, the ocean. Okay. Sodium bicarbonate is just baking soda. Baking soda does dissolve in water too. So the term dissolves is not very educated. It's not very technical. It's like literally, does water surround the molecule and take it into solution? All three of these, that happens, yes? So what if I replace the word dissolves with ionizes in solution? Which would apply to that? Ionizes in solution. 1 and 3, because ionize represents ions are forming. If I said the word solvates in solution, solvate is similar to saying dissolves. So there's all these terms that do mean dissolve, but they don't mean the same as other things like ionize, dissociate. Those are about the only other two. Hydrolyze, things like that. There's all these other terms, but dissolves is a very generic term. So ionizes would only be 1, 3, but dissolves would be 1, 2, and 3. So just know that these two things are slightly different. Okay, so we're going to do chapter 15 in about 10 minutes. Got it? And we're going to jump into 16 because tomorrow we have the pep rally, not in this class, but I know that I need to make sure that we're all kind of on the same board with each other. So we're going to watch a properties video of water first. Watch her take down a couple notes on the properties of water. We're going to do a little bit more review with this, and then we'll be done with chapter 15. You can write it wherever you need to.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, the high surface tension, a high heat capacity, and changes in density based on temperature. Let's take a look at each of these in turn.
Great. I can have a marker out. Go ahead and write down the properties of water. What's the difference between cohesion and adhesion? Anybody? Yep. Cohesion means two water molecules come together. Because it's like co-workers, cooperate, they come together. And what does adhesion mean?
adhesion would be something to non-water. So what does water attract to that's non-water? Plastics out of glass, anything that water can actually, like the meniscus of a graduate cylinder. The meniscus is forming because the water is adhering to the sides of the graduate cylinder, so it's creeping to the sides just a little bit because it's attractive, but it's staying together still at the middle. That's why it's got that dip, and it's cohesive with itself. So that's why it's got two sides of the story. High surface tension, we know what that is. The high heat capacity whenever last unit, and then change density. They're going to go over.
Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions.
Okay, so in this picture, I think you should write or somehow draw an anion and a cation and how the waters interact with them. That's going to be important to understand a bit more about how solutions work. So sketch yourself a little depiction of two ions of different charges and how water orients themselves, the water molecules. So what part of the water molecule is oriented towards the chloride ion, James? I know the positive part. What part of the water molecule, what atom is that? That's the hydrogen part. And the hydrogen has less electrons around it. That's why we show it has a partial positive. And then Eli on the sodium, which is the red part, the negative part that's oriented towards the sodium ion. On the water molecule here, which of the atoms are oriented towards the sodium ion? This one right here. Which is the red the hydrogen or the oxygen of water? No, the hydrogen is what James just said. Hydrogens have the positive charges and they orient towards the chlorine. So the oxygen part of water, which is partially negative, orients itself towards the sodium, which is the positive ion. So it's opposites attract all the time.
This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces, and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. However, unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes.
Okay, so we may have drawn a part of this before, but I would like for you to depict how water's solid state looks different than its liquid state. The solid state has a hexagonal appearance. So you can kind of see it right here. How the water, there are 6 vertices on this pentagon, and I'm sorry, hexagon, and the water molecules are just oriented on those vertices, which just basically mean they orient themselves in that manner, leaving a big gap in the middle. What's that big gap full of? Air. It's just got air between it. It could have nothingness in between, what we might say, because this is the molecular scale. This is really tiny. But if there's nothing there, it's taking up less, there's less mass per volume. So less mass per volume means that it gets less dense, and if it gets less dense, then it floats. And that's why the ice will float, because of this pentagon structure that that's how they solidify, and the liquid water is just freely flowing. So you guys know that ice, we've seen icy lakes. The ice sits on top. There's actually water beneath it. We all remember, like, maybe seeing a picture, I don't know, North Pole, where you got the circle cut out of the ice and they can go fishing, so ice fishing. So we all know there's water underneath it. But this actually maintains the temperature of the liquid water beneath it so that the entire lake doesn't freeze. Because if the entire lake freezes, then all the aquatic life would then also die. So this ice is actually serving almost an insulator to the lake beneath it.
This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms so that they can survive the winter.
Awesome. Okay, we learned so much. A lot of that was review, but I think we're okay there. Tell me what the shape is for water's molecular geometry. What's that shape? Bent. Okay. You remember that these are this is the oxygen, this is the hydrogen, and this is the hydrogen, and there are big lone pairs of electrons here. Do you remember drawing water kind of like this? Way back, right? What are these lone pairs doing to this bond right here? Say again? I heard it. Pushing on it, right? But repelling it. So instead of being a linear structure, it pushes down like this to make a more bent structure, because those lone pairs there are pushing, and that's why these bonded pairs are not able to stay in a linear fashion. That's why it's going to be considered bent. Well, with that disproportionate localization of the electrons, there's a lot of electrons on this picture on the left, and lesser so on the right. That leaves us with a polar structure. So yes, water is polar. And I think that's something we've talked about before, and we're good for in terms of review. Can I move on? Okay, so chapter 15 is a lot of review, people. Trust me. Oh, look. Ooh, hydrogen bonding. These dash marks here, those are the hydrogen bonds. In action. Okay, I know. So I'm going to skip these definitions. The only one that was not on the part of that video was the definition of surfactant and why it's useful in real life. So the way that water sticks together like beads and maintains its surface tension is based on cohesion. And that's just hydrogen bonding interaction that causes it to heat up. Well, sometimes water likes water more than it likes anything else, and we need water to do certain things, like specifically clean. So if we have it sticking to itself more than sticking to other things, we've got a problem, because we're not able to manipulate it so that it can do its job. So what we add to water to stop it from interacting with itself, or to limit some of the intermolecular forces of hydrogen bonding, we add a surfactant to it. And the surfactant's job is to just limit the surface tension that the water has for itself, or the attraction that water has for itself. Well, a surfactant, a great example, is just soap. We use it all the time, right? Shake your heads. Yes. Okay. So the best example I have of surfactant is soap, because soap it's like a Jekyll and Hyde. It's a Two-Face, Scarface. Two-Face?
Yeah,
Two-Face. I don't know why I think it's Scarface. That's the mob. Okay. So, Hardy, what is his name? Harvey. I'm not caught up on my comic book. I'll get there. Okay. So it's got two sides to it, two faces to it. So a soap molecule, I'm going to scroll down for us here real fast. Well, actually, you can see it kind of right here. This right here is a molecule of soap. And there's lots and lots and lots and lots of them, right? Well, this ion over here, this is sulfate, SO4 2-. You don't see the second negative charge there because it's bonded, actually. But this over here is having a charge, and if it has a charge, it acts polar or ionically, okay? So all of this right-hand side is going to be polar. Well, these little dashed, or these wiggles here, are just carbon, bunch of carbon, bunch of carbon, and so forth. That right there, does that scream to you, polar or nonpolar? Nonpolar, okay? So this is the nonpolar side, because there are no charges, there's no metals, there's no ions, there's nothing. It's just a bunch of carbons, which are all nonpolar. So it's the one that brings them together. This side over here, the sulfate side, attracts to water because water is polar, and the nonpolar side, in fact, will attract to things like fats and grease and oils because those things are nonpolar. So that's how we get oil and water to actually mix together, because water stops being so clicky and hanging out with itself, and oil doing the same thing. We make them come together because they attach to the soap, which is like the bridge between them, and that's how we get them to wash down the drain. That's how we wash clothes. That's how we wash our hands. That's how we wash dishes. That's how we get things clean. Because most of the time, oil and water would never mix, but we force them to by this use of the surfactant. Yay! Yay soap! Okay, it solves problems, people. It solves problems. All right, so that's good.
Okay. Let me take a stretch break for a second because we're going to do chapter 16 information.
I'm sorry, we just can't be together. Is it because I'm fat? His face cracks me. And then this one. Sorry, I thought the joke would break the tension. Lol, people. Come on. Okay. Help, I'm dissolving. The bears are insoluble. That's easy for you, say. You're not polar. Oh. Okay. On. Hydrogen bond. Yes, I remember. All right, you're welcome. Okay, chapter 16. We are going to do, let's start with solution solubility.
There's a worksheet right in front of you. This is yours. It's so much. I know.
So we're going to start here. Start sketching according to the data. I know this little black part off the top of the columns are difficult to read, so I'm going to pull that up on the board for you. So your sketches don't have to be beautiful nor incredibly exact. Just start plotting some of that data so you can recognize what a solubility curve is. So here's what the graph the information on the very top. It says potassium nitrate on the first one, barium hydroxide on the second one, potassium chloride on the next one, BaOH2, KCl, potassium iodide, and sodium chloride. We haven't spoken chemistry to each other in a while. We just start using our words again, our names. So basically what is given to you is the temperature and the grams dissolved in 100 grams of water. So on this curve, or on this this plot, you don't have axes. I'm not going to tell you what the axes are, but you can also look at the graph right next to it. See the graph right next to it? What's on the bottom? Temperature. So your bottom axis, your x-axis title will be temperature, and your y-axis will be grams in 100 grams of water. Grams in 100 grams of water. And let's definitely plot the potassium nitrate one, the sodium chloride, so circling the ones I think you should start with. Cover those two. The first and the last.
estimation is good. It's a quick sketch.
All right, I'm thinking you have enough time to get the general picture here. Here's the general picture by a fifth grader. All right, so you have, maybe they might be better than this. You basically have one that's exponentially almost increasing in their solubility, which is that. Ooh, don't say its name like that. Potassium nitrate. Okay, so potassium nitrate, KNO3, was our one that increased pretty exponentially. The one, what was this one? Sodium chloride. Okay, so sodium chloride, over the temperature span, what happened to its solubility? It maintained pretty evenly, right? We went from like 20 to 40 maybe. It wasn't a big difference in its solubility, despite the fact you were heating it up immensely, right? Well, what happened to the solubility of potassium nitrate as you increase its temperature? Like exponentially. So if you increase the temperature of potassium nitrate, it will dissolve a lot more in water. We're going to max out salt water eventually, or sodium chloride in water, because it just doesn't get that much more soluble. So looking at some of the other pieces of information given to you, at the top of the chart, what kind of compounds are those? All these ones we just were working with. What kind of compounds are these? All of them are ionic, right? And in general, what's the trend for the ionics? When you increase the temperature, what happens to the solubility? Generally, you increase, right? So generally, any of these ionics increase in solubility. I don't want to increase ionic. Increase solubility with increasing temperature, and that's for ionic. Well, can you think about a real life example where you have gases in water? Anybody? Gases in water. Well, what kind of bubbles? Like carbonation, like what? Like soda. Okay, so what do we do to keep the soda bubbles inside of soda? Okay, we close the lid. That's a good start. Second? Okay, they pressurize it. Give me more. Where do you store your soda? In the fridge. Okay, that's not just to keep them cold, people. That's to keep them fizzy. So if you have a soda, let's say you have an open can of soda, you put it out in the sun. What's going to happen in, let's say, a day? It's going to be super flat. It's going to be very warm, but it's going to be flat because it's warm. What does the warmth do to the bubbles? It doesn't dissolve them. It makes them, when you say separate, what do you mean? So where do they go? So they evaporate out, right? Okay, so the temperature that you're adding to the bubbles makes them excited. They evaporate out into the air. Therefore, the soda goes flat. Well, if you put that same open can into the fridge the next day, it might be a little bit flat, but it's not going to be as flat. The bubbles should somewhat stay in there because they're
cold and they don't have enough energy to overcome the attraction and like leave the solution. That's going to be something called Henry's law. So if you can assume, let's say we put carbon dioxide as our last component on this graph, make an assumption using your knowledge about the solubility and temperature relationships. As I increase the temperature of a gas, something covalently bound or a gas, what would happen to the solubility? It's going to go down. It's going to be less soluble because there's just not as much stuff dissolved in the water. So that means there's not as many solutes in the solvent. So I skipped a couple things, so I want to see what you guys can tell me first. You did okay. Let's kind of pick back up here, and then we'll see where we are. So information that I just skipped. Oh, do we know the difference between solvent, solute, and solution? Which is the smallest quantity? Solute is always the smallest quantity, okay? It's the smallest one because it's going to be like just like the Kool-Aid. It's the powder that you put in to make the lemonade or whatnot. The solvent, what's the most common solvent? Water. What's up, Kyle? Okay, bye. Okay, and then the solution is the total together. This is the combined effort of the solvent and the solute together. So that's our three main differences, assuming you're okay with that because you did your molarity worksheet with that yesterday. Okay, so the other components that we need to talk about is why do solutions form? Well, they have to like each other enough to actually dissolve, interact, and make a solution. So our rule is like dissolves like. Do you guys remember this? Like dissolves like. That's my song. You already forgot my song? People, just in case you forgot it.
Dissolve! We saw you! Nice. Great. Now we're going to get sued by ACP. The saltness of the water in a beaker today. The ions broke apart in the usual way. The molecules of water kept the ions apart. A salt solution formed, but that's only the start. Homogeneous, the same throughout. Homogeneous, the same throughout. Solids that are polar can dissolve. Solutes that are polar or ionic, that is really cute. Water and unpolar solids just won't mix, but a nonpolar solvent, vitamin E can fix. Like dissolves like polar and polar, like dissolves like non-polar and non-polar, and all the solvent molecules used up. Stuck with the solute ion in your cup. Solutions that you're ready to dissolve for sure. Solubility's been raised for that temperature. Saturation on the line. Saturation on the line. If the cells and water molecules aren't stuck, then more slave can dissolve. Hey, you're in luck. Solution is unsaturated, can't you see? You haven't yet reached the solubility. Unsaturated. Put more in. Unsaturated. Put more in. If you put more solute in, then can be dissolved. Then a supersaturation situation's involved. The aqueous falls out as a precipitate. But the solution is unstable, so you acetate. Supersaturation. Supersaturation. The saltness of the water in a beaker today. The ions broke apart in the usual way. They made it harder for the water boil to freeze. So the fusion temperature changes a few degrees. The ligative properties. The ligative properties. Concentration. Electrolytes have a greater effect on the melting and boiling point of the solution than non-electrolytes. More solute that's dissolved got more effect.
Okay, we're gonna watch the rest of that tomorrow, or when we do collision properties. But you get the point. Polar dissolves, or polar and polar like to dissolve each other. Non-polar and non-polar like to dissolve each other. If they don't have similar IMFs, they shall not. Here, put back their stamp. If they don't have similar IMFs, they will not dissolve in one another, at least very well. Summarize this in however you need to, but like dissolves like is the phrase that means what I'm saying. The fact that oil and water are not dissolving or mixing with one another is simply because they have different IMFs, different intermolecular forces. So if you have, like, for example, hydrogen bonding and hydrogen bonding, then they will mix. But if you have hydrogen bonding mixing with something that's London dispersion forces, they will not mix. So that's kind of what this last example down here is referencing. Sorry, today's an INLO talk slot day.
unsaturated and supersaturated? Yes. You like it? I'm trying to show you that example. All right, who wants to break my heart? We volunteer. That's pretty bad. Who's first one? Me. Okay, so this is like a little hand warmer thing. Okay, so there's like a little there's a little disc in there, and he's going to break it. I'll break it like this. Just set this in there. Here we go. Like this. And like on that little disc in there, it already starts to solidify. All right, wiggle like this, like this, like click it back and forth. You did a very poor job breaking my heart. You got it?
Yeah.
What does it feel like?
Super warm.
It's super warm. Pass it around. See, my heart's full of love and warmth for you guys. Okay, so what you're seeing here, this was a liquid solution, and as soon as you disrupted it, he disrupted it by just going like this and shaking around and clicking the disc back and forth. The solution was not able to maintain its solution liquid form anymore. It started to precipitate out. And as it precipitates out, it actually is releasing energy, which is now we're going to use for bleeding to be a hand warmer. So that actually is sodium acetate that was a previously supersaturated solution. So what does the supersaturation refer to, do you think? What does supersaturated sound like? Oversaturated. Well, what does saturated mean? Huh? No. Oh, well, that is true, but not in this sense. What does saturation mean? Okay, we'll come back to that. Let's do saturation right now then. So here are the definitions, kind of the general terms for saturated versus unsaturated versus supersaturated. I'll let you guys write down some of this first, and then I'll do it. We're going to do the other demos. It's just not cool enough yet. Yeah, there are different types of hand warmers. Hand warmers that are metal-based and they react to oxygen. It makes like magnesium oxide or iron oxide. That makes what's those ones that you shake and get oxygen inside of them, and they create the product which is exothermic. Huh? No. Well, heat. It likes to flow. But the other one, that one's just a solution-based one, it's not a reaction-based one. Actually, one of my students gave it to me a couple years ago. He was a nerd, and he gave me that for a long time. I also got this nice silicone disc when I was a student. So I think you're realizing that saturation in this respect, yes ma'am. Well, I'll come back for it. Saturation in this respect is referring to how much stuff, meaning solute, can be put into a solution standpoint. And it's almost like, a paper towel. So we said saturation with a paper towel means that it can't hold any more water, right? We soak up all the water, it's saturated. Super saturated would be like if it were dripping, right? It's dripping, dripping, dripping. It can't hold anymore. It's too full. And unsaturated would be a dry paper towel because it's got lots and lots of little air pockets still left that can hold the water. So you can definitely relate it back to an example in real life. This is just one that's going to be utilizing this solubility curve, which you have in front of you. We're going to work on 2 of those that you guys have. So saturation is just maximum, I'm just going to say full, okay? Full of solute, okay? It's just a generic term for that. So what would be your term for unsaturated? Not totally empty. We could say not full, right? It's just not all the way to maximum capacity yet, so not full. You can really dumb this down, right? And so we're talking about the solute in the water, the solvent in this case. Supersaturated means that you have heated up the solvent so much you forced it to hold more solute. Because remember, we said higher temperatures generally correlated with greater solubility. So if you actually have to heat it up to do this, to make it supersaturated, and then you let it cool back down. Well, you let it cool down so slowly that solute stays dissolved in solution, and it's just hanging out. But if you look at it wrong, if you sneeze,
if you touch it, it usually precipitates right out of solution. So it's unstable. It's so unstable you say a bad word to it and it will drop out of solution. That's kind of what he did. He wiggled it around and it starts to fall out of solution, meaning precipitate. And we can always detect that because one, we can see it, and two, it sometimes gives off heat. Or it gets really cold, but generally gives off heat. So we're going to see how this graph can show each of these solutions. So on your graph, you guys don't have this one fully done, but you actually already graphed this sodium or this potassium nitrate right here. You graphed something like it, right? So tell me at 50 degrees, what is the saturation point of potassium nitrate? So at 50 degrees, what's the saturation point? So all you do is you go over to the 50-degree mark, you travel up until you cross the potassium nitrate, and you go over here and you see that 80 grams, that's how we would write it, 80 grams of KNO3, potassium nitrate, dissolves in 100 grams of water. So that's the saturation point at 50 degrees. It's very temperature specific. So what would be a supersaturated solution at 50 degrees for the same compound? Great. So all you do is you say, I'm going to put more in than it should be in. So saturation on the line, okay? Supersaturated, it's maybe, I'm going to go 120 because I did it there on accident. So supersaturated is going to be above the line, or above the saturation line, meaning that you got too much in there and it's going to be unstable. So 120 grams and 100 grams of water is going to be an example of a supersaturated one. What happens if I disturb it? What's it going to do? Precipitate out. It's going to precipitate back until it gets to its equivalence of what the saturated should be. So how much is going to precipitate out of this solution? 40 grams, because it's 120 dropping down to 80, so it's going to be a 40-gram difference. Is everybody clear on that? These are usually easy. I just need to do one or two examples. What would be an unsaturated solution at the same temperature? Anything below 80, right? So let's just go, I'm going to draw a dot here. So if I put 60 grams of potassium nitrate in 100 grams of water, you guys said that would be what kind of solution? Unsaturated. So unsaturated is the term that we use to describe that. How much more solute could dissolve in? 20 more grams, because you can go up until you meet the saturation point. Thumbs up if that makes sense. Okay, you guys have this on your paper? There's a graph on the next page over here. Go ahead and complete the questions that correlate with the graph. This graph is just a little bit different than one you graph. All right, let's look at the first couple together. Give me a thumbs up if you got approximately, by reading the graph, approximately 100 grams of potassium bromide. Okay, thank you. So all you did was go to the 80 degree mark, traveled up to solve KBR, and you rolled over here to see what the approximate gram was. Remember, this axis is per 100 grams of water. That's important in the next question. So number 2, how many grams of sodium nitrate will dissolve in 500 milliliters of water, which is how many grams of water? 500, because it's a 1-to-1, 1 gram per milliliters density. So it says on the graph, did we all see that it said 80 grams and 100 milliliters, or 100 grams is how much it should dissolve? So if it were 500 grams, there should be 5 times as much dissolving. So what's that? So 5 times is 400, right? It's just 400 grams. So 400 versus the 80 should be our final answer there. Most soluble 40 degrees Celsius, you just went up to the top value at the 40 degree mark. That's going to be our sodium nitrate. And then the potassium bromide, how much should dissolve at 60? For potassium bromide, how much should dissolve at 60? 85, 90, right? So 85 or 90, but we put 100 in. I'm sorry. We put 100 grams in, so we realize that's going to be super saturated. It's more than saturation point. Okay, I'm going to see if this will work for us. You guys see the solution? What will it look like to you? Clear liquid, right? Clear liquid. Well, I hope, cross your fingers, with the touch of my magic wand, it will no longer be liquid. And is it cold? It's hot. It's not gonna burn you. It's not gonna burn you. Okay, that is what happens. You disturb it, you touch it, you look at it, you tap the glass with a glass rod, you disturb it, it's so unstable, it goes boom, pops out of solution, precipitates back down. Yeah. Well, it's just the magic wand that I like. I have another magic wand. I wasn't sure if this will work. This used to light up. This is what I used to beat my children with. Maybe. You never know. Okay. So we'll wrap up with solutions right now. We won't be able to get similarity in a lot of it, and that's fine. Let's wrap up with solutions, meaning let's finish up our talk on gas, how the gas particles dissolve in solution. So this right here, what would I like you to write down? Let's see here. Reading this, it should be fine. Reading that, the kinetic energy part would be the only thing I would ask for sure you write down. But we talked about this. We talked about how if you increase the temperature, generally a solid is going to increase its solubility. That's just how it works. You add more kinetic energy, it bombards the particles dissolve. But if you have a gas, the gas actually gets that kinetic energy. And if the gas gets that kinetic energy due to the increased temperature, like we say here, the gases don't stay in solution, they tend to escape, simply because they are able to evaporate. And so that's just simply because the increase in kinetic energy allows for evaporation. But we actually have a law for that, and that's coming down here in just a second. So I think the top up here is kind of common sense. So usually, you guys are like, oh, how do I keep the gas in my soda? Put the cap on, right? Well, that's us basically saying keep it pressurized, keep the pressure inside the container. And that's called Henry's law. And I want you to read and write down some of that, and I'll explain. Hot now.
Okay, so pressure, we all know, if you have a soda and you pressurize the top, the bubbles stay inside. So if you increase the pressure, the bubbles stay inside the solution. Well, that means they're considered to be more soluble, so the pressure causes the increased solubility because it's basically keeping the vapor or the atmospheric pressure or the vapor pressure on top high to keep the bubbles maintained in the solution. So when we talk about Henry's law, we do speak of it at a specific temperature because temperature can affect the gases. So when you have two variables going on, you don't always know what's causing what. So we're going to talk about a simple one temperature system. The solubility and the pressure are directly related. So if they're directly related, if I start you off at atmospheric pressure of 1, and I say that this gas is dissolved at 20 grams of gas per 1 milliliter, well, that would be a lot, per 100 milliliters of solvent, okay? So let's say this is what I told you. I accidentally switched those. Okay, so 1 atmosphere is the pressure 1, 20 grams of gas per 100 milliliters of solvent would be solubility 1. What if I said the pressure of the system is now 2 atmospheres? What should be the pressure, what should be the solubility? 40, because it's a direct relation, right? So it should be 40 grams dissolved in 100 milliliters of solvent, simply because it's a double pressure, the solubility should double. So it is a direct relationship. And this is why we try to keep our sodas closed, so the bubbles stay inside down here versus come on top of the cylinder. That's Henry's law. You have one like this in your problem set, so just want to make sure you got this down for yourself. Good? Okay. We're doing that. Give me one last favor. We'll do that tomorrow. Before you leave, I want this. I've already talked to you enough. I want this. I want a picture. You didn't fit. Nobody really got to this yesterday. Picture describing your knowledge of solvents of a solution. It can be funny. It can have lots of variables in it, but I want a picture. You can put this on a separate sheet of paper or on your notes. Doesn't matter. I feel like I killed you guys today. Oh, Maddie. Yeah. So after you get started on that, I'm going to put up reading guide 16 for you so that you guys can write down some of that and you can work together. There's 10 questions off reading guide 16. So I'll put that on the board for you. You okay, Matt?
Yeah.
Here, I'll give you some motivational music.
In the usual way. Water gets the ice apart.
You're like, that's not what I was thinking.
Homogeneous. Homogeneous.